first thing first, we use a compound known as tetramethylsilane as a reference in this case, TMS, right? The tetramethylsilane we have discussed earlier as well. It is a silicon atom which is joined by four methyl groups, right? Okay, this is what is known as tetramethylsilane. You'll see the formula popping up again and again. CH3 4 times. Okay, so in this case, by standard procedure, we assume that tetramethylsilane is the reference. Okay, so with respect to this, we record the chemical shifts of other compounds in this case. So you will always see that the graph starts with tetramethylsilane. I'll give you a general example in this case. You know, you understand how graphs work, right? You're aware of how you have to first of all create X and Y axis. You have to join them together. You have to create a point of origin in this case, right? In this scenario, you understand that, right, Nisa? So
Yes, sir.
all of these points are jotted because you want to standardize the graph in this case. So here also, in order to standardize the graph, because it is a 2D graph, just like a normal graph in this case. But the thing is, there is no particular value where you can start with. So tetramethylsilane has the lowest electronegativity in this scenario. Okay, if you read the statement, it clearly states, okay, why do we use tetramethylsilane? Because according to it is measured against the standard produced by 12 hydrogen atoms, okay, or 12 hydrogen nuclei in the tetramethylsilane. Because the hydrogen nuclei are all in the same environment, only one signal is recorded here, okay. This is because silicon has a lower electronegativity than carbon, and therefore TMS or tetramethylsilane absorbs radio wave in a different region than the from that absorbed by hydrogen nuclei attached with carbon. Okay, this ensures that the standard does not overlap with the signals of any compound under investigation. Is that clear?
Yes, sir.
Okay. So even when you're talking about a simple thing, just as reactivity series, right? You have learned about electromotive force, right? So there is a series which defines certain elements, ions, and then there are voltages or potentials written next to it. So it is also defined on the basis of a control or a reference, and that reference is hydrogen, right? Its particular potential is 0.00 volts. Do you understand, Nisa, what I'm saying?
Yes,
Okay.
sir.
So same thing here as well. Anyways, the chemical shift represented of a proton is defined by this particular formula. Okay. Please understand what is this formula. So here mu and mu naught are basically frequencies of the radio waves absorbed by the protons in the sample and in TMS. So based on this particular formula, we can then figure out what is the chemical shift in this case. Okay. We learned about chemical shift last time, right? Okay. So although the absolute frequency of the signal depends on the strength of the magnetic field, the chemical shift, that is the relative to the standard, stay the same. So no matter where you are, okay, what sort of electric field you're using or magnetic field for that example, what strength of magnetic field you're using, you will always end up with the same sort of chemical shift. Now, this is relative, meaning if let's say if I talk about a table and a chair, so the ratio of table to chair will always depend on the size of the table, right? If let's say you're sitting in a dining table, in this case it will always have 6 chairs, right? So the ratio to that is 1:6. So here also the same thing happens. No matter the size, in this case, size of the graph or the effect of the magnetic field, the ratio remains the same. Clear? Finally, TMS also has some other advantages. It is chemically inert, absolutely inert. It is used as an organic solvent. It can be easily removed from the sample as it has a low boiling point.